Hey, good evening, Anil. Glad you could join in. What's up? How's it going? Quick confirmation. Am I audible and is my screen readable? Awesome. 8847. Thank you. Perfect. Cool. Going good. That's good to hear, man. Really good to hear. Hope everyone else is doing well as well. Welcome to this final lecture on the NLP module. Today, our major point of discussion is going to be the BERT neural network, right? So BERT stands for bidirectional encoder representation from transformers. Quite a mouthful. Hmm. Arun says, going okay, bad patch. So this is the highlight of your day. Okay, perfect. Glad that could be the case. Bad patch, it's okay, man. Like it happens. Um, Everyone goes through ups and downs. The important thing is to not lose our sanity, right? We have to remember why we're here, what we're doing, small things which help us maintain sanity. But yeah, as I was saying, today we're going to learn something which is BERT. What is awesome about BERT is it gives us the power to do transfer learning. So today we're going to figure out why, out of all the models that we have learned so far, BERT is the only one, or transformer-based models are the only ones which allow you some sort of transfer learning. So yeah, that's mainly going to be the this thing. Today's last session on NLP. Yes, Arun. Today is the last session on NLP. I was actually not yeah, yeah, cool. Let's sort of see how this goes. I'm going to try my best to finish everything in detail. If there are any doubts, what we can do is we can go back to Slack. I'm always available, as I said, and I'll be more than happy to address your doubts there. So it's always fun to like one thing that one advantage that you guys have that I did not have when I was studying these things is you have people who are working on the same things, right? So I really want to encourage you guys to form groups and do projects, because the only way to actually learn this stuff is to apply it somewhere, right? Uh, Doing a small mini project by grouping up is a very, very good way to move forward. So there are a couple of students who have reached out to me for project ideas and stuff. So I encourage everyone to do that, because a small project which you're doing on your own, right, which you're owning, that will increase your confidence like anything. I mean, like, and the good thing is like the good thing about these topics is nobody on the planet knows this stuff. So yeah, nobody on the planet knows this stuff. So whatever new things that you will be able to figure out, right, that will be yours, and that is what will set you apart in an industry setting, right? So this is a very good opportunity to sort of learn things through project work. So kindly team up. And once you form teams, if you are interested in knowing what is possible, what can we do as a small project, that you can take my guidance. I'll be more than happy to do that. Okay, so we're 5 minutes into the class. I will start the lecture once I address Deepit's question. Deepit was not able to take the last lecture. Will you be able to follow to some extent today? Deepit, yes. So I'm going to do my best to do a recap. The most important thing that we have from last lecture is the architecture of the encoder, right? So BERT is basically nothing but a transformers encoder. So what we covered last class, I'm going to be doing a detailed recap. You feel free to stop me and ask me questions whenever you need to. And yeah, and we can take it from there. Cool. So Arun's question is, so one query, Ninja Cart and Mintra notebooks in lecture are not uploaded correctly. I see. Arun, can you please reach out to me on Slack for this issue? Like I'll take a look from my end, what can be done. So just one request. Yeah, cool. Okay, guys. So let's begin. Let's understand what BERT is all about, right? Okay. So let's do a quick recap of where we were. Once we have done the quick recap, we'll do the detailed recap. And once we're done with the detailed recap, we can start discussing today's topics, right? So broadly speaking, the business case that we were trying to solve in the last class was neural machine translation. What is neural machine translation? Very simple. If I give you a sentence in one language, you have to translate it to some other language, right? Everyone, I believe, has used Google Translate at some point or the other, right? And we've all laughed at the weird translations it does for Indian languages. Like we make a lot of fun. Like in ISC, we used to keep making fun of the way it translates. So everyone at some point in their lives who have used Google Translate have used a neural machine translation algorithm. Since 2016, the neural machine translation algorithms at Google have been neural network based. So we've all come across these, right? What we are going to see today is how do we implement one using a transformer neural network specifically. Okay. So about transformers, what we covered in last class was two things. A transformer is basically an encoder decoder architecture. Broadly speaking, can you tell me if I give you a body of text, what is the job of the encoder? Like I'm asking you to use the intuition we've built from the RNN and LSTM parts. What do you think is the job of the encoder? Anyone? Think you can use an analogy from our real life, right? Yeah, get a meaningful embedding of the input. So it's like if you're from an engineering background, one day before the exam, whatever you study, that is basically you doing an encoder's job, right? So it's like that. Yes, building the knowledge base, exactly, Anindya. So the job of the encoder is to build a knowledge base. It is to store all the useful information which is there in the input text, right? That is the job of this encoder. And today we are going to do a detailed recap of why this transformer encoder, which uses only attention, which does positional encoding, which implements something mysterious called multi-headed self-attention and is trainable. All these properties, why is it that this encoder does a much better job than LSTMs? This we're going to recap, right? Okay, cool. Then the decoder's job over here is to use this knowledge that we have built one day before the exam and then actually answer the questions in the question paper, right? So the decoder's job is to make use of the representation that the encoder learned to do the final task. The final task can be anything. It can be neural machine translation. It can be named entity recognition. It can be text classification. All the applications that we have studied so far is basically what a decoder is going to do, right? Okay. So just one question about this, okay? Do you really think once the encoder has done its job, okay, do we need to keep running the encoder again and again? Or do we only have to do the decoder part once the encoder has studied? We don't need don't need to keep running the encoder, right? Yes. So this is one of the main reasons why encoder based architectures are you can apply transfer learning to encoder based architectures. The job of the encoder is to make a representation for the text it has already seen. This can now be leveraged for multiple different types of tasks. Okay. So today we're going to study study the decoder part of the transformer. We're also going to see if I just train an encoder and keep it aside, that itself is very powerful. It can solve any type of tasks that you want in NLP, right? Okay. So before I move ahead, there's a query. We have to keep knowledge base on regular interval. Yes, that is definitely there. So the strategy that what researchers follow, right, to handle this problem, that we keep needing to update our encoder. So what people do is they will train different encoders on different corpuses, and then when we are applying them, we have to pick one of those smartly. Okay, so we have to see which corpus or which set of documents this was trained on. Then depending on our task, we will use the one which is relevant there. So we will see an example of this. Okay, cool. So let's move on. So let's quickly do a detailed recap of what we had studied last class. Deepit, this is where you're feel free to ask me if you're not understanding any part here, right? So, okay, cool. So let's see this. This is what the encoder architecture looks like. First, let us trace how the input moves through this architecture. So let's see this. So my entire sentences are now going to be as inputs over here, right? What we are essentially inputting over here is an entire body of text, okay? How do we represent text using vectors? The hint is over here. What do we do to represent text or whole sentences as vectors? We use typically word to vec, glove, and we usually keep this fixed. This is not something we want the encoder to learn as it's doing its job, right? This is something we want to keep fixed. So typically in transformers, we will take something which is pre-trained and we will use this as the input embedding. Okay. And the same input embedding will be used by all parts of the transformer. Right now, only one part is visible over here, input embedding. When we study the decoder, we will see that the same embedding is used to interpret what the decoder is outputting, right? So this word-to-vec glove is fixed for the entire transformer architecture. Okay. So once we've done this, uh, what was the main advantage of LSTMs and RNNs? The main advantage was different words generated different hidden states, right? So in some sense, in LSTMs, RNNs, GRUs, all these architectures, the position of the word was very well encoded. Okay. But now, since we are giving the entire sentence as input, right? We also have to somehow let this neural network know what position this word that I'm inputting is coming at, right? So the way this is achieved is through something which is known as a positional encoder. Okay, this is done through a positional encoder. What is a positional encoder? It is basically a sinusoid vector plus the embedding vector that I'm going to get from word to vector. So Deepak, just a quick recap for you. The way this is done is I will use this kind of a formula. Okay, I will use this kind of a formula, P of pos comma 2i equal to sine of pos by n to the power 2 to the power 2i by d, right? This looks like a very complicated formula, but what it's doing is very simple. Let's visualize this, okay? So let us say I have my first word. This I'm calling P0, okay? So what I basically have to do is, for the first word's glove embedding, I have to add a sinusoidal vector. What is the basic requirement when I'm adding two vectors? The length has to be the same, right? So if my glove embedding gives me something like a 300 length vector as the output for the first word, what I now have to do is I have to add one sine kind of wave to this. So the question is, how am I going to generate the sine wave? Okay. The way I'm going to generate the sine wave is the d that is there in this equation, that is going to be 300 because that is what glove gave us, right? It's a 300 length vector. So this d is going to be 300. This I over here is actually telling you what to put in this sinusoid vector. This I is now going to control the index of this, okay? And what I want you to notice here is for 2i, that is for even numbers, okay? For even numbers, this is going to use a sine of this value. And for odd numbers, it is going to use cos of this value, right? So the way I'm going to generate it. So in this illustration, we're only having 4 positions, not 300, okay? So if we had just 4 length vectors, how will we do this? We will take these two sinusoids, okay? What I want you to notice is, as and when we keep going ahead, right, along this dimension, the frequency of the sinusoid is increasing. So this has some frequency, right? This is, so look at here. Roughly over here, 2 cycles are getting completed. Over here, for this same position, only 1.5 cycle is getting computed, right? 1.5 cycle is getting computed. So the way I'm going to generate my positional vector is by using these sinusoids like this. How are positions defined? So like this. So the green parts that you see here that I'm sampling go to the P0 vector. The red parts go to the P1 vector. The pink parts go to the P2 vector, and the blue parts go to the P4 vector. P3 vector. And like this, I will have my positional encodings. Okay. Once I've done my positional encoding, I finally go and give it to one block of the encoder, transformer encoder architecture. Okay. So whatever I've highlighted in yellow over here is just one block of this transformer encoder. What is happening over here? Let us see. Okay. So first of all, I want you guys to notice this arrow which is coming out. What is going to come out here is basically like a matrix, right? So if I have 4 words and each word has a 300 length representation, I will have a 4 cross 300 matrix, right? So this arrow that you're seeing here is like a 3 cross 400 matrix. 4 cross 300 matrix. What are the dimensions? The dimensions are going to be the number of words over here is going to be the first part. The length of the glove vector that is coming out is going to be the second part. So this matrix is now coming here. Okay. What I want you to notice is it is splitting into 3 parts over here, right? Because it is splitting into 3 parts, these are nothing but the query, key, and value parts of our attention module. Okay. Does everyone in class remember how attention works? there were those 6 steps, right? So we have these query and key vectors. We use these to generate what is known as attention weights, and then we apply the attention weights on the value, and then finally this value is what is given as the output of this attention head. Okay. So what's happening here is I have a multi-headed attention over here, and I'm calling it as a multi-headed self-attention. So what is the meaning of this? The meaning is since it is self-attention, the matrix I'm going to use for query, the matrix I'm going to use for key, and the matrix I'm going to use for value are all going to be the same. Okay, that is point number 1. Point number 2 is, yes, and Deepith, you're exactly right. This is going to be like a context vector for each word. Okay. So the value output that I'm going to get from this is going to be that context vector for each word. The main difference between this and what we had studied 2 classes before was this one. Okay. It's this. I now have to add some neural network part over here, right? I want to do some training over here. I don't just want to keep that attention like this. So the question is, how do I make it trainable? Okay. Here is a quick example of how to make this trainable. So if this is my matrix, look at this. This is my matrix where thinking machines is there. Thinking is the first word, machines is the second word. So I have 2 rows. And in this example, I have 4 length vectors for my globe vector. So you can think that the globe is giving output dimension as 4 over here. Okay. So this matrix is the input to this multi-headed self-attention. What I'm now going to do is, for the same input, I'm going to pass it through 3 separate dense layers. Okay. I'm going to pass it through 3 separate dense layers. The output of these layers are query, key, and value. Okay. Once I get these query, key, and value from these dense layers, this is what I'm going to apply my attention on. Okay. So I'm going to take an inner product between my query and my key. That I'm going to apply softmax on. Once I apply softmax, I will get this Z0, which is my attention weights. I will multiply this with my value to get, my bad, query and key. So I will get my attention weights. I will multiply those attention weights with V0 to get Z0. So Z0 is the final output after applying the attention weights calculated using Q and K on V0. Okay. So this is how I will get my Z0. Now, once I get my Z0, remember that this is a multi-headed attention. What does that mean? It means that, let us say I want 8 different attention heads over here. I want 8. It's like I'm asking 8 different people to sit and pay attention to these input words that I'm putting there. In this example, it is 2. So let us stick to 2. What I'm going to do is the same thing. I'm going to pass through another 3 set of dense layers. Okay. So I will have one output from the first head, the second output from the second head. These I'm going to combine, okay, into a matrix. I'm going to pass it through this linear layer over here, and the output of this is what I'm going to finally get as my Z. Okay. So think of it this way. I asked 2 separate people to give me attention weighted values. Okay. 2 separate people to give it. I applied a dense layer over here to take this input and give me the output in the same size as my X vector. Okay. So the input and the output of my multi-headed attention is going to have the same dimensions. That is what we have to remember here. Okay. Yes. So Anil's question is, Z0 is the output of softmax for head 0, right? No. It is the output of softmax multiplied by V0 to get Z0. See, what is the final output of an attention block? It is the context vector, right? How do we get the context vector? We get the context vector by multiplying the attention weights. What are attention weights? It's the output of the softmax. So this attention weight is going to be multiplied by this value over here, and that is giving me Z0. Okay. Is that clear? Yes. Yeah, Z0 is the context vector. Yes, Anil, absolutely. So the main thing I want you guys to note here is X and Z, the output of the multi-headed attention and the input to this have the same dimensions. How are we getting that same dimension? We're getting it by passing it through a linear layer, which will do that size change. Okay, cool. So now I'm going to get the output over here. So to this output now, I'm going to simply add the input that I sent over here, right? I'm going to send the input over here. I'm going to perform an add and norm operation. Add and norm operation is very simple. Whatever output is there over here. So let's quickly see if it's over here. Do I have it? No, I don't. Let's visualize what add and norm looks like. One moment. It's after this, right? Yeah. So look at this add and norm layer. So I'm getting one Z matrix as the output of this multi-headed self-attention. I'm getting this X matrix from my input. I'm simply adding them both and I'm applying layer norm. Layer norm is doing one very simple operation. Okay. It is going to take the mean of these two it's going to take the mean of this sum. It's going to take the standard deviation of the sum. It's going to subtract the mean and divide by standard deviation. That's it. That's all this layer norm does. This is now sent forward. So now each row over here will be corresponding to one word over here, right? Remember the dimension of this is the number of words over here. So now again, we will split that part and we will pass each of those rows through a single feed forward network. After we pass each individual row of this output through a feed forward network, we will again have an add and normalize, same idea, right? There's a skip connection which is going from this to this, same idea. We'll simply add this and the output of these feed forward and we will produce this kind of an output, right? So this is how this entire transformer encoder block works, okay? And what has computer vision taught us? Is one of these enough or should we keep cascading many? Should we keep adding depth or is just one enough? No, right? We have to cascade many of these. So what we will do is, so in the original transformer paper, right, where they trained a transformer to do machine translation, in that paper, they used 6 of these blocks to take it forward. Today, when we're studying BERT, we will see that we can use 12, 24, how many ever we want. And the more we use over there, okay, the more we use over there, the better performance we will get. Okay, that is what we will see. Okay, Azhar's question is, can you please explain the feed forward network part? Sure. Okay, let me explain it through an example. Okay, so what I'm getting over here, right, Azhar, this is the output of the multi-headed attention. Right? Okay. Indradeep, I'll come to your question. First, let me answer Azhar's question. So this is output of the multi-headed attention. This is the Z matrix. Once I take this Z matrix, right, what I'm going to do is every row over here is corresponding to one word in my original input sentence, right? My original input sentence in this example was thinking machines. It's a phrase. It's not a sentence, but whatever. I have 2 words over here, right? So what I'm now going to do is I'm going to split this output into 2 vectors. Okay, I'm going to split this output into 2 vectors. Each vector will pass through a feed forward network. Okay, each vector will pass through a feed forward network. You can think of this feed forward network as nothing but a dense layer, right? Is this making sense? So this dense layer will basically be a square matrix. It will not change the dimensions of this. Okay, it will just be a square matrix. The output of this is again gathered in the form of one final matrix of the same shape, and then we will do add and norm on that. Is that clear, Azhar, how this is working? Cool. Okay. So that's basically how this is done. So the main thing of note over here is, for this operation, right, we will have to fix the length of our inputs. That is one thing that we will have to do later on. So we will see how to do that when we're actually implementing. But yeah, that's one drawback of this, doing it this way. Arun says, so like we have 10 words, we need 10 for feed forwards. Yes, Arun. If we have 10 words, we will need 10 feed forward layers at this stage. That is the problem, right? So there are ways of dealing with this. We will see, right? Okay. Indradeep, now I'll address your question. The last feed forward network is to have more trainable parameters. Yes, right? It is to have more trainable parameters. Mainly think of it this way. Once I have already paid attention to it, what if I want to shift the attention weights again, right? What if this attention layer has not captured enough information to store? So we're giving this one more chance. This feed forward network is going to give one more chance to reweight these attention values, and then it will send it forward. That's the key intuition here. Okay, cool. So this was the detailed recap of the encoder part, right? This is the detailed recap of the encoder part. If everyone has followed me so far, just hit a yes right now. If you have any further questions, please ask me right away. right? Please ask me questions now about this, because if we're clear on this, we can now move on to understanding the decoder part of this architecture. Okay, so this was the encoder. Now let's go and focus on this big thing that we're seeing over here. Okay, this big decoder that we're seeing over here. So what I'm now going to do is I'm just going to get a image of this so that I can discuss, right? So let's extract this part of the network. Let's take it there and let's analyze this now. Okay. Okay. Before I move ahead, I just want to tell you guys the main agenda now. Now that we have done our recap, okay. Our agenda is today. First, we're going to look at the decoder architecture, which I'm going to be doing right away. Then we're going to go and conceptually see what BERT is. We're not going to go to the code part yet. Okay. Once we're done with the decoder, we're going to go and see conceptually what is BERT on top of this. Once we've understood both of these ideas, okay, BERT is not very difficult to understand if you understand the decoder architecture. So once we have covered BERT, we will go and see a transformer implementation using transfer learning for machine translation, right? And then we will use BERT for a different task. The code of these two is kind of common, which is why I'll discuss both of them towards the end. But the main things that I want to cover today are the decoder architecture and what BERT is. Okay, so let's do it that way. Okay, so I'll just keep this accessible so that if anyone asks me questions about attention, I can come back here. This figure is very good for understanding how that attention mechanism is working, right? So if ever you want to rote learn one figure, it is this one. Okay, cool. So now let's focus on the decoder part. Okay. Okay. So remember how I told you the decoder's job is basically to build a knowledge base and provide some type of context vectors, right? So the final output of this decoder architecture is going to be two matrices. The two matrices are going to be query and key matrices. We hope that the entire knowledge of our input text, right, is somehow stored in this query and key parts. Okay, that is what our hope is. That this query and key vectors, which are coming as the output of these blocks, they will essentially be enough to store whatever knowledge we need. Okay. Now we'll see how that is coming over here. So whatever output that is coming from the encoder, right, it is actually connected to the decoder at this stage. Okay. So encoder outputs, which are majorly the key matrix and query matrix, sorry, not value, key and query matrix, broadly speaking, are coming at this stage. But before we reach this stage, let us see what else happens, right? Okay. So whatever I'm going to now discuss is basically for the decoder stage. Okay. What we have to now understand about this decoder is something. Okay. First of all, we have to understand how is the decoder called. Okay. Do you guys see that the output over here is output probabilities? This output probability will help us generate one word at a time. Okay, this output generates one word at a time. Okay, this decoder is not a network which will give you the entire output in one go. That is the main thing that we have to understand about this. So although the encoder, whatever information we were sending forward, that was being read one at a time. For the decoder, this will generate one word at a time as the output. So let me give you an example. Let us say the output of the decoder is this: start, this is a cat, end, right? So can you guys quickly tell me how many times will the decoder run for this? 6 times, right? 6 times. N is the perfect answer, Azhar, like in general N. But over here, to generate this sentence as the output, right? Start, this is a cat, end. This decoder will have to run 6 times. So we have to now do something special over here, right? Okay. Encoder can use paragraph 2. Encoder can use paragraph 2. Encoder only uses paragraphs, Anil. Encoder will see the entire sentence at once. It will not do one word at a time. Okay. Indradeep has one question. Encoder gives key and value matrix or key and query matrix. It gives key and query matrix, not value. Okay. Indradeep, think of it this way. Don't you think value is like the output part of the attention mechanism, right? It's like the output part. Key and query's job is to give us some attention weights to apply on this value. So whatever context information we're storing, right, from our text, that will give us key and query, not values. Yeah. So Anil, yes, it can take the whole document at once. It has to take a whole document at once. Yes. Arun says key textbook query exam question values are learning. Exactly, exactly. Right? Exactly, exactly. I love the analogy there. Okay, cool. So let's move on. Now let us try and understand how this decoder will start generating this. Okay. Now to activate the decoder, right? To activate the decoder, it's very important for us to start with this start token. So the first time we are running a decoder, the input word over here, the output word over here, right? The output word that we're going to give here is this start word. Clear? The first time I'm getting values out of this, I'm going to give the start tokens. So what I'm going to do is I'm basically going to take the start token. I'm going to get its output embedding from glove or word to vec, whatever it is, right? From that, I'm going to get the vector for that. I'm going to then apply positional encoding on this. Right? I'm going to apply positional encoding on this, and then this is again going to pass through a multi-headed attention now. Okay, this is going to pass through a multi-headed attention. There is no difference between this multi-headed attention and the multi-headed attention that we have just studied. Okay, there is no difference over here. Whatever we studied over here, multi-headed self-attention, same thing is happening here. Do you guys understand why this is important? Why this is important? While generation? I just want to make sure the intuition is hitting everyone. Okay. Think of it this way. Usually when we are translating things, right, don't we do it one word at a time? Don't you think it is important for us to pay attention to what we've already generated and then fill in the blanks for what is left in that sentence? So same thing over here. I'm going to start with the start token. I'm going to let my network figure out how much have I already completed, right? How much have I already completed? Anil, yes, similar network for both. You're absolutely correct. It's the similar network for both. I'm going to use this attention mechanism to see how much of the task I've already completed. Then I will continue with the forward task. Okay. So this part of the network, right? This multi-headed attention and norm, this is basically for my network to understand how many words have already been generated, how much of the task is still left. Okay. That is this guy's job. Once we have passed through this, right? Once it has passed through one of these layers, what is going to happen is this. The key and the query matrices, the key and the query matrices are coming from my encoder, right? This is like my knowledge base. The value, right? The value I'm going to get from the output of this encoder block. So the job of this block, right? The job of this part of the network is to give us value vectors. Okay. So if we have understood this concept clearly, let me ask you one more question. When I'm generating, so let us say I have already finished generating start this is, okay. When I'm asking my network to generate this, the third word over here, right? When I'm asking my network to generate this, do you think I will need a new value vector or will I use the same value vector that I had from before? I have already generated this part, right? So am I going to need a new value vector or do I have to keep the same? Okay, so let us understand why, what is the correct answer here, right? So I got both, right? I got answers. So Arun says it's the same value vector. Indradeep says it's new. So the correct answer is it is going to create a new value vector here. Why? Because now I have to let my network know that start this has already been generated, right? So this is what is kind of important. Every time I have finished generating one set of outputs, right? I'm going to come back and I'm going to repeat this operation. I'm going to repeat this operation. So every time my value vector is going to change over here. This changes for every new word. Okay, this changes for every new word which is generated. Right? This is essentially going to change for every new word which is generated. Okay, cool. Now let us see how this progresses. So Anil's question is, how will that be generated? Let us see, Anil. So for now, let me do one thing. Let us for now assume just that we have the start part. Okay. Let us assume we just have the start part. We will do a forward pass and we will see how this is reused. I will explain that at the end. Okay. Okay. So now I have my first value vector, which is coming from this word start. I have applied this attention mechanism on it and I have generated this value vector over here. Right? I've generated this. The key and query from the encoder is going to be used over here to this multi-headed attention thing. I'm again going to do an add and norm operation after that. Once I do an add and norm after that, again I'm going to pass it through a feed forward, add and norm, okay, layer. This is going to continue. So you can think of this whole thing over here, right? This whole thing over here you can think of as a decoder block. Okay. So imagine that this decoder block is multiplied n times. So we can have 20 decoder blocks, 40 decoder blocks, depending on the accuracy that we need, right? Okay, cool. So this is what we are going to have. Now, once we have passed it through so many decoder blocks, we have to pass it through a linear layer finally, a softmax layer, and it will give me an output probability, right? So if my first word was start, let us say after doing all this computation, my network decided to give me the word this, okay? So now let us pay attention, okay? Now that this has happened, now that start and this have both been generated, I'm going to pass both of these as inputs to this attention layer. Okay, I'm going to pass both of these words as inputs to this attention layer. So I'm going to now repeat the whole computation with start and this as the input over here. Okay, once I finish this whole pass, then it will give me something like is. Then I'm going to take all three of these, I'm going to pass it again as input over here, and it will generate a. Then I will take all four of these, encode it as a, pass it over here as the input, and it will generate the next word cat. And once I have passed this also, it will give me the final token, which is end, right? So are you guys getting an intuition for how these passes are happening for the decoder to work? Okay, one person has understood, two people have understood. If anyone has not understood, guys, please feel free to stop me and ask me, right? Okay, some people have not understood. I will answer your queries, right? Okay. Before I go there, Azhar has a question. Encoder and decoder blocks look similar. There is one main difference, right, Azhar? The multi-headed attention in the decoder uses key and query from the encoder. That is the main difference. The key and query for this decoder blocks is coming from the encoder. That's all. Deepit's question is, different languages have different structure of sentences. So is that info being captured from positional encodings? No. Think of it this way. When I'm doing neural machine translation, right? When I'm doing the task of neural machine translation, the multi-headed attention over here and these feed forward layers over here, this is what is basically giving me a relationship between one language and another language. So internally, concepts are being stored, okay? How the concept is being mapped to the language of the word is being taken by the decoder. So think of it as a two-stage process. First, I'm mapping words to context, right? That context is some vector. Then the decoder's job is to figure out, with this context, what is the correct word to give in the other language as output. So the translation part is happening on the decoder side, not on the encoder side. Okay. Okay. So Arun's question is, but after start going the second pass, aren't we forgetting our early input? We're not, right, Arun? We're not. See this, our early input is coming here, right? See, whenever we're passing things over here, don't you think the whole step is being repeated? So aren't we now going to generate an attention weight for whatever is there over here? So the context vector that is there for the first part is coming from this. It's coming from this output. You see this, you see this orange block over here, right? The job of this orange block is to create a context vector using whatever has already been generated, right? Make sense? Okay. Indradeep's question is, so decoder execution has a sort of time angle like LSTM? Yes, yes. Decoder execution has a time component over here, just like LSTM. How are we keeping track? We're keeping track by passing whatever has been generated again and again through this decoder. Okay, like that. Anil's question is, how are we passing different inputs like start this? Is it like 1 cross 300, 2 cross 300, 3 cross 300 matrices? Anil, you saw how we did it here, right? So think of it this way. Every time we run the decoder, right, we're adding one row to this input matrix, Anil, right? So whatever word was, so imagine this, the first time only thinking was there, okay? And then I compute attention with this matrix. Then next time I will have thinking machines. So I will do all my operations with this. Then I will have thinking machines this, right? Then the next word will come here, right? Then it will do all the operations with this matrix. So like this, it will keep happening. Yeah, it's going to work like this. So if your question is, aren't the dimensions of my matrices changing over here? There is a special way to handle this, and I'm coming to that just now. Okay. If you're wondering, won't my attention dimensions dense layer weights change every time? It will change, and how to handle that, I'll show you. I'll show you that now. I just wanted to delay that for the end because this is a little confusing, right? So I just wanted to first show you how the generator works, how the decoder works. Now that we've understood this, we can focus on this detail. How are we going to handle the changing dimensions of these matrices if every time the length is changing, right? Okay. Guys, what was the solution in LSTM? What was the solution in LSTM? Remember in LSTM, we had a problem, right? For all the inputs, we had to give a padded sequence because otherwise there would be more importance on short sentences, less importance on large sentences. So the solution was padding, right? So the solution was padding. Same thing is now going to appear here, okay? So Anil, the way we deal with this problem is that we pre-decide the length of the output, okay? We say no matter what, the decoder has to give us 100 length output. Arbitrarily, we can choose this as 100. Then what we do is, wherever we don't have output, right, for this part in thinking machines, for the rest of the 98 parts, we will simply put zeros over here. We'll simply put zeros over here. That way, these matrices are now going to be fixed. Okay, these matrices are going to be fixed. Okay, is that clear? Yeah. So this is how we deal with this problem. Basically, what's happening now is I will make sure whenever I'm giving my input to my decoder, initially it will have only one row which is non-zero. The rest of the rows are going to be zero. I'm going to carry one forward propagation and it's going to work. Then next time I'm going to put the word predicted in the second row of this matrix over here. And then I'm going to pass it, right? This is how we deal with this problem. There is one tiny issue which comes when we're doing this, right? Okay. So there is one problem here. Don't you guys think if there are only zeros over here, there is no point of this? Okay, so wait, I'll give you an example of this. Okay, I'll give you an example of this. I'll take this example and I'll explain this further. So there is a slight nuance when implementing the attention weight computation in this part. Okay, in the multi-headed attention where key and query are coming from my encoder and my values are coming from this, right? Here is the problem, guys. I'll first explain the problem. The value matrix that is coming here, it is like this, okay? Imagine it's like this. Let us say we have fixed this input length to 4, okay? But it has only generated the first one. So let us say this is the embedding corresponding to my word which is start, okay? This is the embedding corresponding to my word start. Now I have this embedding over here, but these are nothing but zeros, right? These are nothing but zeros. When I'm calculating softmax probabilities, right? Do you think I should take these zeros into account? What do you guys think? Okay, I'll tell you what are the repercussions. If I take these zeros into account, right? What is the probability of this going to be? The probability of this is going to be like 1 by 4, right? It's going to be like 1 by 4. No? Okay. Why not? Yes, right? So let us say I'm passing this matrix through my softmax. The probability of this word is artificially coming to 1 by 4, something like 1 by 4, right? Because e to the power 0 is 1. Remember that. E to the power 0 is 1. So the denominator is actually going to have 4. But only one value is there over here. So this is going to give 1 by 4 as the attention weight. Now this is wrong, right? So we have to fix this issue now. So let me clearly write down what the issue is, just so that everyone is on the same page. Okay. The issue is softmax will artificially put 1 by 4 as the weight. And if you think about it, these will also be 1 by 4, right? Something like 1 by 4. So softmax will artificially put 1 by 4 as the attention weight when we use padded inputs. So how to solve this problem? Yeah. So now the thing is, we have to replace the zeros over here, right, with something more meaningful. Okay. Can you guys tell me something? E to the power what will give me 0? E to the power what will give me 0? If you guys don't remember, I will just quickly plot what the e to the power x graph looks like, right? E to the power x graph looks like this. Right? Minus infinity. Perfect. So e to the power minus infinity is what gives me 0, right? So logically speaking, don't you think I should replace all these zeros over here with minus infinity? Don't you think that will solve this problem? Don't you think that will make sure I'm correctly assigning probabilities based on the length which is already generated? Okay, cool. So this is exactly why we use something which is known as a look ahead mask. Okay. This is exactly why we use something which is known as a look ahead mask. Now, let us take this example into consideration. Okay. Let us say that my input sentence was in French and my job is to translate this to English. Okay. My job is to translate this to English. So what we are seeing over here is actually like it's actually like it's the value matrix that we're seeing here. This is the value matrix, okay, guys? Not the key and the query. This is the value matrix. But the problem with this value matrix is if my first word was start, right? Remember, this has not yet been generated. My network has not yet generated this, but I have this value matrix which is coming as the output of this orange layer over here, okay? The question is now, how do I adjust this so that the correct softmax is applied over here? What I have to do now, whatever part has not been generated, right? Whatever part has not been generated, that I have to replace with minus infinities over here. So that once I apply softmax, right? So I will basically take this, this kind of a matrix. I will create this mask based on how many things I have not yet generated, okay? So think of it this way. If the first token is start, then the value matrix that I will give as the output over here, right? This value matrix that I'm giving as the input to this one, this will be masked as follows. I will add this matrix to this one so that now my value looks like this, so that even when I apply attention weights on this, right, these will still remain minus infinity. And when this is used to generate the attention weights, this is also going to be used in the softmax part, right? So this will basically solve the problem of wrong weights because parts of the text which have not been generated, right? This will solve that problem. Okay. So this is the job of this look ahead mask. So let us quickly uh, summarize all the computation which has happened in this part, this multi-headed attention part. All the computations is summarized in this diagram. Okay, cool. So before I go there, I'll quickly answer Deepit's question. Shouldn't all columns other than start be minus infinity? No. The reason for that being, if I have 1 minus infinity, right? Do you remember that when I'm computing my attention weights, I'm doing an addition on this? I'm doing an addition column wise, right? So when I'm doing addition column wise, it is anyway minus infinity. So it doesn't really matter. So it's taken care of by this structure. So the way they do it is this way. So when I'm applying softmax, it gets taken care of. Okay, cool. Now let us quickly revise everything that has happened inside this multi-headed attention over here. Let's recollect this. Okay. So I have my query and key vectors which are coming from my output layer, encoder outputs. I'm passing this through a linear layer. I'm going to apply the matrix multiplication between my query and key. Then I'm going to apply a scaling, right? Remember, we have to scale it by the dimension of the vector that we are getting over here. So we're going to apply that scaling. Then we're going to apply a mask to this one. Okay, we're going to pass it through the softmax and then this value. So just one update. This is not the value matrix. This is rather the query into key matrix. This is the output of the query. So this is that Q transpose K by under root D, right? This is that matrix over here. So on this, I'm going to apply my mask now. What is the mask? It is simply an addition of this part. Okay, simply an addition of this part. This is going to pass through the softmax and it's going to come to this matrix multiplication operation here. All this matrix multiplication operation is going to do is whatever weights were generated over here get multiplied column wise to, they get multiplied row wise to this value matrix. Then this is then passed through a concatenation layer, which is then passed through a linear layer to give us another value matrix. Okay. So this is now going to generate one more value matrix. Next time I'm going to generate another word or next block, right? Remember where this is just one block. We keep repeating blocks. Each block in the decoder's job is only to generate one, what do you say? Each block is only going to generate one value. Okay. That's the basic idea here. Okay. So I just have a query. I didn't understand what is 0241. I didn't understand that. Anindya, can you clarify? Didn't get the query. But essentially, this is how many decoders. Oh, okay. Please ignore. Sure. Okay. So this is how this is going to be generated. Okay. This is essentially how this is going to be generated. So now that we've understood how this decoder block is working, right? Now that we've understood how this is working, if we want to see how end-to-end this works, right? End-to-end performance. So what we can do is, let us discuss what the end-to-end performances of this is going to be. Okay. Indradeep's question is, I did not understand how we stack decoder if we have applied softmax. Okay. How am I stacking my decoder if I've applied softmax? So let me make this more clear. Right? I'll just make it more clear. Whatever is happening here, right? This part, right? This computation that I just discussed with you, okay, is describing how this is working. Only this multi-headed attention part is being expanded over here, right? After we do the multi-headed attention part, we still have to pass it through add and norm. We still have to pass it through feed forward. We still have to do one more add and norm, and then it passes through this, right? Yeah. So that's what. I'm sorry. I'm sure it was a confusion for many people. Thanks for asking the question. So whatever we have seen here in this recap is only an expansion of this multi-headed attention part. Okay, where the query key is coming from the encoder. my value is coming from the previous part, the orange part, and then, right? Okay. So think of it this way. Once this part has executed, right, this will give me new value vector, which is again going to be passed through this kind of a thing. Okay. It's again going to be passed through this kind of a thing. Right? Okay. So that's the basic idea here. All right. So imagine that this is now going to be repeated over here. Imagine that this block in pink gets repeated 5 or 6 times. Finally, whatever is the output then goes through a linear layer, then a softmax, then we get output probabilities, and then we get one word at a time generated. Right? Okay. So this is essentially how my decoder architecture is going to work for my transformer. Let us quickly now go and see how well this performs compared to RNNs, LSTMs, and other architectures that we've seen so far. Let us quickly check that. Once we've checked that, we can see how to apply it to solve a problem like machine translation later on, right? Okay. So just want to sort of highlight this thing over here. One moment, I have to come here and plus it. Yeah. Okay, cool. So cool. Now let us see how the transformer architecture performs in relation to the RNN LSTMs that we have studied before, right? That is what we are now going to see. The time complexity per layer for an RNN or LSTM architecture is going to be n into d square. Why n into d square? N here is the number of words I'm generating, right? D square over here is the dimension of the word representation. So every time I want to generate output from my RNN LSTM, right, I will actually have to do so many operations. Whereas, and the number of sequential operations that I have to do is big O of n. In the attention, I have to do n square into d operations to generate one layer, right? So in the decoder part, I'll have n square into d. Why n square into d? Let's understand this. N square because I remember we are generating these attention matrices, right? So n square number is coming from the self attention that we're applying. The d number over here is coming from the fact that we have to take these attention weights and multiply it with a d-dimensional value vector, right? So n square into d is coming from, n square is coming from the self attention part. The d is coming from the value multiplication part. And the number of operations that I have to do is big O of 1, right? So overall, the time complexity of my attention transformer is going to be better than my RNN, okay? So computational complexity of my transformer is already better. Let us see how it performs. So what I have over here is the quality comparison for the English to French and English to German tasks. Okay, this is English to German. ENDE is English to German. ENFR is English to French. ENDE again is English to German. ENFR is English to French. Okay, BLEU that you see over here is nothing but a number which tells us the translation quality. Okay, we're going to study this blue score over here. So it's basically something which it's basically a score which essentially measures how well the translation has happened, right? It uses a bunch of factors. It uses a bunch of factors to measure this. So the exact details of this is not something I'm going to discuss, but what it basically does is it checks whether the translated sentence follows grammatical rules. So there are various grammatical rules in the other language. Based on each rule that it follows, it gets a +1, and then the average of that is reported as the blue score. So broadly speaking, that is how it is done. What we're now going to see is how are these blue scores for different types of algorithms. So what I want you to notice here is these are basically all types of LSTM plus attention mechanisms. Okay, these are LSTM plus attention mechanisms. These are also LSTM plus attention types of mechanisms, and these are just transformer models. Okay, what I want you to notice here is we have two transformer models here. One is the base model, the other is a big model, right? The big model is basically where I'm using many more blocks in my encoder and decoder layers. The base model has fewer blocks. So think of this as 12 for the big one and 6 for the base model. Okay. Now, of course, since we already know that more the depth, better the performance, we see that Transformer Big has the best performance over here. Okay. Transformer Big has the best performance for English to German and English to French translations. So transformers actually outperform all other architectures that we have already studied so far. Okay. The computational cost is also seen over here, right? So the number of floating point operations is what is reported over here. What we'll pay attention to is the 10 to the power 18. We're going to pay attention to the order of magnitude. So order of magnitude wise, see that for all of these ones, right, it is 18, 19 or 20, right? It is differing based on the language. So for French language, you need 10 to the power 20. For German language, you need 19 and like 19 or 18, right? Over here, I need 20 or 19, whereas this is 20 or 21. Comparatively, these numbers are actually much better than all of these. So this justifies that not only am I getting good results, I'm getting those results faster also, right? So that is why overall transformers are what are ruling the current scenario. Okay. If you ever want to solve a task in NLP, the first thing you should consider is a transformer architecture. How do you consider a transformer architecture? You have to use this amazing library by Hugging Face. Okay. So guys, Hugging Face is a company which works with open source code. Okay, what this company basically does is it will go to every paper which is important, which is considered as important by the research community. It will get the code from them. It will uh, it will basically compile it in a nice way, in the sense that it will make the outputs of that code accessible to you, and it will give you access to a library where you can easily import those results and use them for transfer learning. So you can think of Hugging Face as a company which is making life easier for you to apply transfer learning. Okay. So they have their own library called Transformers library. The way we install this library is through this command, pip install transformers. If you do this, then you get access to this Transformers library, right? So this, once we have installed this library from Hugging Face, what we have to do is we have to go and see which model we want to use as pre-training. So broadly speaking, the steps that we will take to implement transformers is we will first install transformers library from Hugging Face. We will go to the literature and see which paper is currently the state of the art. Okay. We will take the state of the art model. We will use transfer learning to adapt it to our task, and we will create our applications based on transfer learning for whatever we want to solve in the industry. Okay. So this is essentially how we do this. The exact details of this I'm going to discuss together, like all the code for transformers and BERT I'm going to discuss together. So what we can do now is we can take a quick 5-minute break. And if anyone has any questions, you can private chat me those questions. I can try explaining it during the break. Once we come back from the break, we will start our discussion on BERT. Okay, we'll start our discussion on BERT. And what the nice thing is, the code that we're going to use for BERT and the code that we're going to use for the transformers are very similar, because the basic steps are the same. We're first going to import from the Hugging Face library. We're going to get the network that we want, and then we're going to train it for the task that we want it to. Right? So those steps are common, which is why I will explain the code of both of these together. Okay. So is it okay if we take a break now? Quick check with the class. Can you hit a quick yes if you are okay with the break now? Okay, cool. So let's take a break now. Once we come back, we will study BERT architecture and how it was implemented and everything. So once we discuss that, we can go for the code examples. Okay. So let me quickly bring the timer here. Guys, if you have not understood any part, right, I encourage you to interact with me through private chat during the break. Okay. So please do that. For the rest of you, I will see you after the break. And we're back. Can I get a quick confirmation if you guys are back? Okay, few people are back. Nice. Okay, four people are back. Interesting. And two people were trying to make me laugh. Guys, should I wait till more people are back or should I continue? If you're back, please hit either yes or no. Let's do this one more time. Okay, maybe a few more people are back now. All right. Okay, three people are back. Awesome. Four people are back. Is it the same people? No, more people are back this time. Okay, awesome. Perfect. So we have enough people. Now let's talk about this new thing called BERT. Okay. So hopefully now we have understood what goes into a transformer, right? Transformers, the basic idea behind a transformer is whatever is happening in an RNN, instead of using those things, we will only use attention mechanisms to do everything that is there, right? Uh, that is the main design of a transformer. Now, the major issue with transformers is this separation of this encoder and decoder part, right? One of the issues with the transformer is we are separately doing something for the encoding part, separately doing something for the decoding part. What people thought was, if encoding is only required once, can I not pre-train that encoding and keep it ready? Something like that, right? Can I not pre-train an encoder and keep it ready? There was another school of people who thought encoding will keep changing. So I will explain this using this example. Okay, let us talk about this transformers encoder and decoder part. Transformers. Okay, transformer. Oh, what am I doing? Yeah, transformers have two parts. One is the encoder part, the other is the decoder part. Let us understand at a functional level what are the jobs of these two components. Okay, encoder's job is to study a corpus and uh, store context information. Okay, the job of the decoder is to use context information to answer questions. Okay, and I just want to explain this school of thought because if you understand this one small thing, right, you will be able to appreciate a lot of other architectures that you will see apart from BERT, right? Okay, so guys, don't you think more than one encoder can exist, right? You can have multiple encoders for multiple different sources of information. It's like studying different subjects for your exams, right? So for a computer science BTech course, for example, you will have one textbook for computer networks, you'll have one textbook for programming, one textbook for operating systems, like that, right? So think of it this way. If I train different encoders and I keep them aside, it is like I'm training my model on different sources of information, right? So multiple encoders can be trained for different sources of information. Okay, can I now I want everyone in class to think a little bit. Okay, does it make sense to have multiple decoders? When what would each, so if I have multiple decoders, what would be the job of each decoder? So let us say I have decoder 1, decoder 2, and decoder 3. What is the major difference between these decoders using our analogy? Can I say that my decoders are basically task specific? Guys, am I still audible? Ha, okay, I'm still audible. Okay. Cool. So Indradeep is perfect with his answer. Each decoder is for a different task. So task 1, task 2, task 3. Okay, task 1, task 2, task 3. So this is how NLP researchers right now view this architecture. Okay, you take a transformer, you look at it and you look at its encoder separately, you look at its decoder separately. Different encoders will store context information about different sources of information. Different decoders will apply that context information to solve different problems, right? Does this make sense to everyone? Okay. So let us say I only take the task of, question answering, right? So task 1 could be Q&A, task 2 could be named entity recognition, task 3 could be translation, machine translation. Okay, fine. So based on our knowledge, right? Based on our knowledge of GPT. Okay, so let's take the example of GPT. What is GPT? It's a generative pre-trained transformer, right? Generative pre-trained transformer. Since it is doing a question answer task, do you think GPT mainly contains an encoder or a decoder? Which one do you think GPT should contain? It should have only the decoder, right? So think of, no, you're absolutely right. All of you who said decoder, you're absolutely right. GPT is an example of a decoder only transformer model. Okay. Think of it this way. GPT will use different encoders for answering questions about different tasks. So if it is answering a question about computer science, it will use a computer science textbook. If it is answering a question about maybe something like philosophy, it will use a philosophy textbook. Okay. So that is why it makes sense for GPT to be a decoder only architecture. Okay. GPT is a decoder only architecture. Same way, if I have an encoder only architecture, the encoder only architecture acts as a textbook for my GPT. Okay. But the network that we're going to study today is an encoder only architecture. So BERT basically falls in the encoder only part. Yes. So Arun says adding new knowledge. Yes, exactly. So Anil says for K and Q, GPT like architecture will use. For key and query, will GPT like architecture use? Yes, yes. So it's like this. GPT will basically act on keys and queries coming from different sources, but the text generation, the act of generating sentences which humans can understand, that part was trained using different techniques. Okay. So what GPT people focused on was how do we build a network which can do question answering very well. What BERT people focused on was how do we build a network which can store information very well. Okay. So that is a major difference between these two approaches. So right now in the literature, you will have a lot of models which are encoder only. You will have a lot of models which are decoder only. You will have a lot of models which are encoder plus decoder. You will have some models which don't use either. Okay. So if you go to these Medium blogs which discuss current research in NLP, right, you will see them using this keyword called encoder only architecture, decoder only architecture. I don't want you guys to get confused there, which is why I'm simplifying this idea using this analogy. Okay. Think of the encoder as the person who's studying a textbook. Think of the decoder as the person who's actually writing the answers. Okay. As humans, we have to be both. But when it comes to neural networks, we can separately classify these two types of tasks. Okay. So today, if you go and read in the literature, you will see that BERT is an encoder only architecture. GPT is a decoder only architecture. If we're clear about this part, right, we can move on to studying BERT more thoroughly. Can I get a quick yes? If you understood what I mean by encoder only models and decoder only models? Okay, cool. Yes. So Indradeep says, so in GPT training, they use encoder while training only. Indradeep, yes. So the way information is fed into GPT, right? It's kind of complicated. Like we will be discussing this in detail in the future classes. Like there is going to be an advanced NLP kind of module which is being designed right now. We will discuss this in detail there. For today, what we're going to do is we're going to see how the encoder only side works. So yeah, Anil's question is, how will the decoder get the info to complete the task like Q&A? The decoder will get information to complete tasks with, so that is what, right, Anil? We can either use a pre-trained encoder to give this as give inputs to this, or we can use some other strategy. What strategy GPT uses, we'll be discussing in a different class. For today, let's focus on the encoder part. Yeah. Any idea when that module will be available for us? Indradeep, it's difficult for me to predict right away. I'm contributing to that, but I'm not in charge of that, no? So I don't know about the deadlines. So we'll let you know though. It will be announced and it will be made available to everyone. So you can sign up for that. Don't worry about that. That will come. That module will mostly be taken by Verma sir only. So he's in charge of designing the content for that. So you'll be interacting with him for that. Okay, cool. So now let's come back. Now let us focus on how do we train a network so that it can encode information which is there in a given textbook or a given source of information. What is the NLP word for source of information, guys? What is the NLP word for it? Corpus. Okay, perfect. So this is how we pre-train a transformer architecture to store context information with respect to a corpus. So let's discuss this now. The main difference between BERT and the encoder we have seen so far lies in the first word of this BERT. The first word is bidirectional, right? Do we understand what bidirectional is? Do we understand what bidirectional is? We do, right? It is a way for me to encode information from the front as well as the back. We've seen this bidirectional word coming in LSTM's part, right? So BERT architecture is like we are going to take this encoder architecture over here. We're going to have one encoder for the forward direction. We're going to have one encoder for the reverse direction. Then we're going to combine the outputs of both of them and then do something with it, right? Then we're going to do something with it. So think of a bidirectional transformer as something which is first looking at things in the forward direction and then looking at things from the reverse direction and giving us context from both of them. So that is the bidirectional part in the BERT framework. Okay, cool. So now let us see what business case we're trying to solve with this. So you're a data scientist working in a medical research publication company. Hundreds of articles are being published every day. You want to basically classify these documents according to the diseases, right? So what you basically want to do now is identify what all diseases are being discussed in this paper. Manually reading these articles and identifying diseases is a laborious process. You've been asked to train a machine learning model which can automatically do this. Okay. So you want to find all the diseases which are being talked in the document. Can anybody tell me which of the tasks, NLP tasks that we have studied so far, right? Which of those tasks is best for this? It's NER, right? Named entity recognition. It is actually NER. Why NER? Because what we want to identify is what are the diseases being talked about in a text, right? So this is an NER type of problem. You can think of, like, initially you can say that, oh, it could be a binary or multi-class classification where we're taking each word and asking whether it is a disease or not. But that way of doing things will not allow us to make use of context information, right? So it is better to frame this problem as an NER problem. So today what we're going to do is we're going to train an NER model using BERT, where we're going to use the encoder of BERT, which is pre-trained. We're going to use it as it is. And we're going to fit some network. The decoder part is what we're going to design from our end. We're going to connect both of them and then we're going to solve this problem of NER. Okay, cool. So why is BERT SOTA? So what does SOTA mean? It means state of the art. So currently BERT is the best way of doing this. BERT is currently, or at least not currently, I think right now there are bigger versions of BERT. Back in 2019 or 20, BERT was the best encoder to use for these kinds of tasks. Okay, that's the basic takeaway from this. Okay, before I go ahead, I want to answer Indradeep's question. Can self-attention be considered as inherently bidirectional? Since for each word we are paying attention to all other words, whether they come before or after the word of interest. Indradeep, yes, inherently self-attention is bidirectional. but this can change if you change the task which is going there. Okay. So I will explain this when I discuss how to train BERT. I will explain this. Okay. I will just take this. No. But we're only using in one direction. How? In only direction how? Arun, I'm coming there. I'm coming there. Just one moment. I will come to why I say it's bidirectional. It will become more clear when I explain how BERT is trained. Okay. For now, I want everyone to focus on why BERT is SOTA and how it was able to achieve it. Okay. BERT has been outperforming almost all benchmarking NLP tasks, right? Because the way it's pre-trained is with a rich corpus of data. So it's like when we look at the data set BERT is trained on, we'll be like, wow, BERT knows so much, right? And it was able to achieve SOTA results because of this training with a very large corpus. Okay. So the corpus, right? Okay, so this is an explanation of what BERT is. BERT stands for Bidirectional Encoder Representation from Transformers released by Google. BERT only uses encoder portion of the Transformers architecture, which is why it's called Encoder Representation from Transformers, right? So essentially, this is my Transformer architecture. I'm only going to extract this part, okay? And I'm going to create many different types of so I'm only going to extract this part of the network and I'm going to train this. Okay, how to train this we're going to come to, but what I want you to notice over here is this. There are two versions of BERT which are being talked about. One is BERT base and one is BERT large. The difference here is in BERT base we use 12 stacks of this encoder. In BERT large we use 24 stacks of this encoder. Okay, so the BERT large results that you're seeing here are with 24 encoder layers. The BERT base results that you're seeing here are with 12 encoder layers. Okay, that's what we have to understand over here at an architecture level. So there are various ways in which RNN and BERTs are different. We pretty much know all of these. So I'm going to be skipping this for now. If you guys have time, please look at this part in the notebook, right? But this is kind of obvious, the comparison between RNN and BERT. We have discussed this a little bit last class, so we can skip this part. So now we'll come to how BERT is trained, okay? Because this is an encoder, it stores some sort of knowledge about our corpus. How do we train this to store knowledge on our corpus, okay? So there are two possibilities, right? We can either make this a word embedding model or we can make it a pre-trained model. So let me just quickly give you an example of both of these techniques, okay? So do you guys remember your recommender systems classes? Do you remember how we used to create embeddings using matrix factorization? Yeah, okay. Okay. On the other hand, we had CNNs, right? Which basically looked like this, right? So this is a CNN, right? In a CNN, we were able to get embeddings, right? We were able to get embeddings. Do you remember how the output of the layer just before the dense layer is the embedding, right? Okay. But we were also able to apply transfer learning on this part, right? We were able to take just this part and use it for transfer learning. Okay. So were we able to apply transfer learning in any way from this matrix factorization approaches? Did we ever talk about transfer learning from matrix factorization? Not really, right? Okay. So guys, this is the major difference between word embedding model and pre-trained model. Word embedding model is something which gives you an embedding for your words, whereas a pre-trained model not only gives you embeddings, but it can also be used for transfer learning. So now can you tell me, is BERT word embedding or pre-trained? Which one is it? It falls under pre-trained, right? It falls under pre-trained. Yes, it falls under pre-trained. So you can say that BERT is both because it is pre-trained and it can give you embeddings, right? So that is why you can say that it is both. Okay. the way we generally use BERT is we will keep this as, so BERT is like this equivalent. So in a CNN, everything before the dense layer was the pre-trained part. Similarly, whatever BERT will give us is like the pre-trained part. Okay. There are different versions of BERT. So you have something which is known as BioBERT, which is pre-trained on the corpus of medical domain data. You have LawBERT, which is pre-trained on corpus specific to legal domain. The BERT which is there in the original paper, right? This is trained on entire Wikipedia. Okay. So everything that is there in Wikipedia is used to train this. And one more data set is used. I kind of forgot. I'll just see which one it is. So BERT is essentially trained on multiple multiple data corpuses. So let's quickly go and see what those are. It is Wikipedia and one more. Okay, 1 minute. Oops. Pre-trained on Wikipedia and book corpus. So there is, PubMed, no, not PubMed actually, Anil. PubMed would be the medical corpus, right? That would be for BioBERT. But the BERT, which is released by Google in their first paper, right? That was pre-trained on Wikipedia and book corpus. So book corpus is like a bunch of freely available books. Wikipedia, we all know. So it was essentially trained on such a huge corpus. So this is roughly 3,300 million words, right? If you add these two up, this is like 3,300 million words. And BERT was actually trained on such a huge corpus. Once again, I want to remind you guys, as individual engineers, we will never be able to reproduce these results, right? Because to train this, the kinds of computational resources you require is huge. Okay, it's very huge. So the best we can do is hope that there will be some company which will pre-train this and give it for free. And then we can take that and we can use it for different things. That's the basic idea. So, okay. Now, Indradeep's question is, so someone created labeled corpus from entire Wikipedia corpus for BERT training? Yes. Yes, Indradeep. They did not create a labeled corpus. I've still not come to how we are training it, right? Let's discuss that now. I've still not come to how we are training it. So now let's discuss that part. Cool. So we talked about what BERT is. We talked about what is used to this thing. Now, how was BERT pre-trained? Right? Now let's focus on how was BERT pre-trained. So BERT was basically trained on two tasks: predicting the mass. Okay, let me explain both of these. Predicting masked words is exactly like fill in the blanks. Okay, let's take a couple of examples to see this. Today morning, I went for a tooth removal to my dentist. Today morning, I went for a dash removal to my dentist, and the label over here is tooth. Okay, did you go to school today? Did you dash to school today? The label is go, right? So this is what is known as masked language model recognition. Okay, so MLM, the short form is MLM. You see it over here in masked language modeling. So this task is known as masked language task. Can you tell me, Indradeep, to do this task, do I have to really generate labels? Can I not randomly take a sentence? Can I not randomly pick one word to remove and then train BERT to replace that? Yeah, mask was added automatically, right? Yes. So these kinds of tasks are known as self-supervised tasks, where I'm asking my network to take a data set, I'm creating a dummy task for it to solve. We are not actually going to apply BERT to do something as simple as predicting masked words, right? So this is known as self-supervised learning. So the first task that BERT was predicted to the blanks kind of thing, which is masked language modeling. Next one is next sentence prediction. Okay, next sentence prediction is like a binary classification tasks. The input is going to be a sentence. So the input is going to be a sentence and one more sentence. So we have two sentences which are given to BERT as an input. What BERT has to do is it has to tell me if sentence 2 comes after sentence 1. Okay. Can this also be done very easily? Do we have to work hard to generate this kind of data set? No, right? We simply pick a sentence randomly. We pick another sentence randomly. If this sentence came after this one, then we say true. If it came before this one, we say false. Okay. So BERT was basically designed in two stages. First, it was trained to do masked word recognition. Then it was trained to do next sentence prediction. So think of BERT as an encoder, which was trained with one decoder first and then another decoder first. But then what we kept was just the encoder part, and we threw away the two decoders which we used to train this encoder. Does this make sense? Is everyone following so far? How BERT is pre-trained? This is basically the summary, guys. You take the encoder model, you apply separate decoders. Okay, the first decoder will do fill in the blanks. The next decoder will tell me if this sentence comes after that. Once I'm done with this training, I'm only going to keep the encoder and I'm going to get rid of the decoders, and whatever this encoder is, that I'm going to give you as a model to use for transfer learning, right? This is basically what BERT is. It's an encoder only model. Okay. So this diagram sort of shows you how training data and label generation is done. It is basically what we just discussed, right? For the fill in the blanks, we randomly select word and ask BERT to fill it. For next sentence prediction, we randomly pick two sentences, give true, false. Yes. Indradeep's question is, for next sentence prediction, do we use some kind of contrastive learning? The loss which is there in BERT, right? Is it contrastive? Yes, I believe the BERT loss was some sort of contrastive loss. I don't remember exactly though. The best source of information would be the paper, right? So let's go here and figure out. Okay, while it's loading, let's move on a little bit. I will come back to this question, whether the loss function which was used was contrastive or not. To the best of my knowledge, it is. I just want to confirm once. Okay, I'll confirm that. Just remind me towards the end of the class. I'll confirm this. Okay, cool. So let's move on now. Let's talk about what is bidirectional about BERT, right? When we're doing a fill in the blanks kind of task, right? It is important for me to have attention from forward words as well as previous words. Okay, it's important for me to have attention from forward words as well as previous words. OpenAI's GPT, right? It only has information about the previous words. It does not have information about forward words. So this is basically what is bidirectional about it. So what I want you to understand over here is this. When I'm doing bidirectional encoder design, what will change is, so it is not like I will need two separate networks. What will change is how I'm calculating my attention over here, right? Let us say I want to mask a word. What strategy can I use to mask that word? What strategy can I use to mask this word? Can I use something like this in my attention mechanism to mask it? Yes, right? So this is how BERT's attention layers are adjusted. Okay, so BERT's attention layers are adjusted through this kind of a mask when we are doing the fill in the blanks kind of training. Okay, so this is basically how it is done. It is not like we'll have one separate encoder for the forward direction, one separate encoder for the reverse direction. We will use a masking strategy to implement this part. Okay, so yeah, so essentially this is how BERT is a mask. So for this reason, BERT is called a masked language model, because we're using masking to implement this bidirectionality. Okay, the masking is what is being done to implement this part. It's not two separate encoders. Okay, cool. So this is like a short recap of transformers. Since we just discussed transformers, I'm going to be skipping this. Now comes the question, okay, we have understood what the architecture of BERT is, right? Architecture of BERT is very simple. It's the thing that we did a detailed recap of today. Now the question is, how do we actually train this? How do we give the embeddings? How do we do the positional encoding? How do we do all these steps for BERT, right? So let's quickly discuss those parts. So so now coming to what has to be done before we can pass stuff to BERT is this part, right? So guys, whenever I'm providing my inputs to my embeddings, right? Before I actually give my input to my embedding, I have to do something which is known as tokenization, right? Tokenization. In tokenization, do you guys agree that every unique word will get a unique number? The process of tokenization, Is it not simply assigning some index number to the words which are there in my input? It's just that, right? Okay, cool. Now, what happens is BERT does tokenization a little bit differently. Okay, it divides. So each token in BERT, right? Each token in BERT is basically not a word, rather a word component. Okay. So first look at this word. Parachute is a word in itself. There is no meaning if you separate para from shoot, right? Not much meaning is there. So parachute should ideally be tokenized as a word in itself, right? But for the rest of it, paraglide, paragliding, scuba diving, scuba diver, scuba dive, all of these words. So let's focus on these two. These two words can be broken down further, right? So the para part of this is like the parachute version of gliding, right? The para part in paragliding is again the same thing, right? So the way BERT's tokenizer works is that it breaks down words into component parts. And the fact that it's a component is indicated by this double hash over here, okay? So the way BERT would tokenize parachute is it will call it a single word. The way paraglide will be tokenized is para will be one token, hashtag GLI will be the next one, double hashtag DE will be the final one. Okay. This makes sense because if you look at it, gly followed by ding is a different word from gly followed by DE, right? So this is essentially how BERT internally takes care of word forms. Okay. So that is what's unique about the BERT tokenizer. So BERT does not use the default tokenizer that we've been using for all the tasks so far. It uses its own tokenizer. If you guys want to understand how the tokenizer was trained, how it was created, you can refer to the paper over here, right? It's given in detail over there. But for us, what's nice is we simply have to run these two sentences to be able to use it. These two lines. We say from transformers import BERT tokenizer, tokenizer equal pretrained BERT base uncased, right? Do lowercase equal to true. Okay. So if we simply run these two lines of code, we can get access to this very smart tokenizer. And you can play around with this to see how it will tokenize different types of words. Okay. Cool. Now, moving on, what are the different types of BERTs and how do we apply them, right? So essentially, the original paper of BERT gave us 4 different models. 2 we have already seen, okay? Guys, 2 we have already seen. We've seen BERT, just one moment, I'm scrolling up. Yeah, we have BERT base and BERT large over here, right? The difference there was the number of encoder stacks. Now, apart from that, there is one more level of complexity here. You have BERT base uncased. The meaning of this uncased over here is that it will convert all the tokens to lowercase and then the training is done. So BERT base uncased is where it uses the same tokens for the uppercase as well as the lowercase. BERT base cased will actually include the information of uppercase or lowercase over here. Okay. So you have 2 separate models now. BERT base uncased, BERT base cased, BERT large uncased, BERT large cased. All of these models are basically what we can use to do all our transfer learning. Okay. So this BERT base uncased that we use here is basically coming from this model of BERT. Okay. So these are essentially what the different types of BERT models are. The major applications are sequence classification, question answering, token classification, and these links will basically take you to ways for you to import these models. So if you simply go and say from transformers import TF model for sequence classification, it will automatically give you a pre-trained model which you can use for whatever applications you want, which is extremely cool, right? There is a single library which can give you access to so many different models which are out there, which is why Hugging Face is really awesome. Okay. So if you ever guys feel that, there is so much out there, I don't know how to learn these things, you can go to Hugging Face. These guys have amazing documentation. So if you want to understand the broad areas which have been addressed with various papers, right? Hugging Face is a very good place to sort of go. So for example, you can find task guides over here, which will tell you, which will give you example code for each of these types of tasks. So each of these pages will basically be example codes. Okay. So I highly encourage you guys to go to this web page and check it out for yourselves. In the meantime, let us see how to actually do this, right? Okay. So now what we're going to discuss is the code aspects. So whatever I've covered so far is everything that you need to know about BERT. We don't have to worry too much about the exact training of BERT and how it is carried out, because again, it is not practically feasible for us to do it, right? However, there is a diagram at the end which sort of gives you an idea of what all computational resources are required. Okay, so let's quickly scroll down there and see that. Okay, okay. So you have different versions of BERT over here. What they have given here is the training time and computational resources. I just want to take you through this. Okay. So BERT itself was trained with 8 V100 GPUs for 12 days. Okay. To give you some context, Google Colab Pro, right, will at max give you access to 1 V100 or 1 A100. It cannot give you access to more than that. So if you have access to only one of those, how many days do you think it will take for you to train a model? If you have only one V100, 96 days, right? 12 into 8. So that is roughly how many months? Will that be 30, 60, 90? That will be slightly upwards of 3 months. So if we wanted to do this in a free way, we'll have to use Google Colab's free version. No. In fact, Google Colab Pro version also will not give you multiple, right? So we'll have to use Google Colab Pro version and train it for 3 months to get BERT model for ourselves. So this is why I'm saying it's not feasible for individuals to train this. Look at Robert. Now this is even more crazy. This used 1024 V100s for one day, right? 1024 V100s for one day, which is 4 to 5 times more than BERT. And this is like going to take us years with free resources. So again, not feasible. This takes 8 V100s for 3.5 days. This is much lesser than BERT. So maybe we can try on our own training something like distal BERT. By the way, the code of all of these are available. If you want the training code, you literally have to just go to GitHub, download it, and get it to work, right? So this is available. Just to run that code, it will take us so much time, but yeah. And then you have ExcelNet, which uses 512 TPU chips for 2.5 days, which is 5 times more than BERT. So ExcelNet Robert is out of picture. BERT and distal BERT we can train individually with some difficulty, but yeah, that is the basic that is the basic disadvantage. Now, what is good is we can take a pre-trained BERT model and adapt it to a new textbook, right? That is possible. And those kinds of exercises will take much lesser days than this. So my advice to you is when you're out there in the industry and when you're applying these algorithms to solve real world problems, right? Always keep in mind how much time it takes to train from scratch. As far as possible, always go for transfer learning. Okay. Okay. So that's what I wanted to highlight. Now let us come back and focus on the task which is at hand. Okay. The task which is at hand over here is NER. We will come back to this NER once we have solved the problem of neural machine translation. Okay. So what we're now going to do is we're quickly going to see how to use Hugging Face to solve the problem of neural machine translation. Then we're going to see how to use the same library to load a pre-trained model of BERT and adapt it for an NER task. Okay. So now over the next 10 to 20 minutes, let us quickly run through the code. Again, it will not be possible for me to highlight each and every part of the code in detail. I'm going to be skipping stuff which I feel like we've discussed many times in the past, right? So I'm going to be skipping that. Once again, guys, if you need help understanding any of this, I'm available. Please don't hesitate to reach out. The advantage of Scalar is that we're a community, right? You're always free to approach me and ask me doubts. If I'm not free, I can point you to other people. So that's the idea. Okay, cool. So now let us quickly see how to use the transformer library to implement a transformer to do this thing, to do machine translation. All right. Okay. Cool. Just one moment though. Okay, cool. Fine. So now let's go do this. So the first thing we're going to do is we're going to install this library called datasets. This datasets library is essentially something which has many different types of NLP datasets. Okay. This library is responsible for keeping track of different types of data sets. This library called Sacre Blue is the library which is going to give us the blue scores, right? Blue scores are something which tells us how well is a sentence translated from one language to another. For those of you who know a little bit of French, the word sacre bleu basically means God damn it. It's a bit like a curse. So this library's name is a bit funny for French people. But literally it means sacred. So sacre means sacred, blue means the color blue. So sacred blue is the literal translation. But in common language, this is God damn it. So I just found that funny. So I wanted to share that with you. Now, this is the most important library for us, right? Pip install transformers. This is what will give us the Hugging Face library on transformers. And we'll be using this to do all the implementation that we need to. And we're specifically going to install one dependency which is known as transformer sentence piece. So this sentence piece is going to have a sentence encoder, right? So we're specifically going to download this sub package from transformers. Once we do that, what we're going to do is we're going to load this data set called KDE4. Okay, the data set KDE4 basically contains a huge corpus of I'm still here. KDE4 contains a huge corpus of English to French translation. Okay, English to French translation is what it has a huge corpus for. The size of the labeled pair is this much, right? Isn't this big? There is 210,173 English sentences with their corresponding French translations. Do you think this data set is big enough to train a transformer? Okay, awesome. Cool. So now let's use this data set to do all our translation work. First thing, of course, we're going to do is do train test splitting, right? This is an example of what the split data set looks like. So look at this. One phrase is text cursor movement. In French, it is movements du cursor de texte. If there are any French people in the audience, forgive me. I don't know how to speak French well, so I'm murdering this. What's interesting is numbers are going to be kept as it is, right? So numbers, dates, things like that are going to be kept as it is. So then you have reload the namespaces from the server. This overrides any changes. Then you have recharger less or whatever. Okay, I'm not even going to bother reading this, but this is the equivalent French translation, right? Then you have credit card tracker, tracker de card de whatever. Okay, blah blah blah. So this is what a data set looks like. Okay, cool. So okay, yeah. By the way, guys, can you guess where this data set is coming from? Don't you think this is like coming from documentation pages? Somebody basically went to libraries which have documented in French as well as English. They've done web scraping on that, right? Doesn't it look like that? So yeah, so we kind of can guess where this is coming from. Now what we're going to do is we're going to load a pre-trained transformer model. Okay, we're going to load a pre-trained transformer model. This transformer model was trained on a different data set. So it was trained on this Opus MT ENFR. Okay. And the name of this model is Helsinki NLP. We're going to load this model using this function. So guys, this pipeline function is the most important function in the transformers library. So whenever we want to load a pre-trained model, we have to make use of this pipeline function. The first argument that this takes is the task that we're looking at for, and the model checkpoint is going to be the name of the specific model that you want. To understand which of these is possible, you can go here and you can look at this. So all the first entries, right over here, the first entries, which is the type of tasks that we can do, that you can see over here in this part of the documentation. And once you click on it, it will show you what all it has. So there is one green list like this. Okay. So these are all the models that you can sort of load. Okay. So this is all the models that you can load. Cool. Let's go to translation, and I would just want to show you where that Helsinki is, right? So this is, yeah, somewhere here. So it's one of these architectures that we're loading over here, right? Okay, cool. So once we do this, it successfully loads the model checkpoint. And what we're going to do is we're going to use this pre-trained model. We're going to see how this pre-trained model performs. Okay. First, we're going to see how this pre-trained model performs. Then we're going to apply transfer learning to adapt it to our data set. Okay, cool. So now let us see this. So we have this TMP data, which is basically from our data set right now. We're picking the 172nd example. So unable to import one using the OFX importer plugin, this file is not in the correct format. So impossible D whatever. So this is the translation, right? And this is the original French text. So it looks like it's mostly correct, right? So here we have plugin, here we have module. Then here we have different words over here. Although this looks like it's a different form of this, right? So it looks similar. And the rest of it seems correct. So this model is already able to do quite a decent task on this. But what we're going to do is we're going to retrain this now. So the rest of the code is going to show you how to carry transfer learning on this model. So let's run through this now. So first we're going to load the tokenizer. So from transformer, we're going to load auto tokenizer. Specifically, we're going to load the tokenizer part from this pre-trained model. Okay. So auto tokenizer dot from pre-trained, if we run this function, it helps us extract the tokenizer which was used for this task. Now, pre-processing one sample using this tokenizer, right? That looks like this. Okay. So essentially, what is printed over here is essentially what the tokenizers tokens are, right? For this. So this is the original sentence. If you notice, these are essentially all the tokens which are extracted from it, right? So here you have the wrong targets and you have the actual target. So this is just an example of how the tokenizer is going to work on a French piece of text. Okay, cool. Then we're going to see how the pre-processing is going to be done. We are setting our max input and target lengths. Okay, and we're making sure that our data has only those lengths which we want. Okay, we're going to set up the tokenizer and we're going to create this pre-process function, which is essentially going to do the tokenization part using this which we have just extracted. Okay, cool. Now we're going to do our own model. Okay, sorry, my bad. So guys, whatever I have discussed so far is just how to load a pre-trained model. To do the training part, right? We're actually going to train from scratch. Are we training from scratch though? 1 minute, let me check. So model checkpoint is being initialized here, right? Where is my model checkpoint? Yeah, this is my model checkpoint is initialized here. Yeah, no. I'm doing transfer learning only. I'm not training from scratch. Okay. So now the question is, how am I going to apply transfer learning on this model? So the class that I have to import from transformers is this TF auto model for sequence to sequence LM. Okay. How do I know this is what I have to do? I have to go to this documentation. I have to click on translation. And over here, it is explained what I have to import, right? So over here, it will be explained what I have to import, right? So these things will be explained in this documentation. So if you're wondering for your own tasks how to do this, remember, this is your best guide, the transformers library. Okay, cool. So I have my model, which is basically this one. I'm loading a pre-trained weight over here. I have my data collator, which is essentially going to apply tokenization and all the pre-processing steps, right? For that. Anil, I didn't understand the no. Can you explain? Oh, the no was for am I doing training from scratch? Okay, got it. Okay, cool. Cool. So now let's move on. So first, what I have to do is I have to basically use this data collator object to convert this into encoded sequence, right? So always the first step when we're dealing with text is convert it to a set of indices. So what we're seeing here is the set of indices after this data collator has applied tokenization over here. Okay. Then we're going to create a training data set and an evaluation data set over here. We're going to do the usual things. So this is standard Keras. We are setting the number of training epochs as 3, number of training steps as length of this data set into number of epochs. We're setting an optimizer. Interestingly, the optimizer which we're using is coming from this transformers library only. Okay, there is this function called create optimizer over here coming from transformers. We have to use this to create the transformer and the schedule. Once we have this optimizer and schedule, we apply model.compile on it. Once we apply model.compile on it, we run model.fit. So basically here I have been running this textbook since morning. We have 3 steps. It took roughly about 2 hours per epoch over here to train this. Okay, it took roughly 2 hours per epoch. After epoch 1, the loss was 1.0627, then 0.79, 0.685, right? The validation loss is 0.88, 0.82, 0.80, right? So roughly speaking, can I say that my training is going well? Can I say that my training is going well? Yes, I can, right? The loss function is reducing, validation loss is also reducing. So my training is going well. Now, what we'll do is we're going to take this model, okay? We're going to take this model so we had saved a model saving thing, right? So we're going to now take this model, we're going to apply the pipeline, which is translation, and then we're going to apply this one. So yeah, so guys, what is nice about that or what is different about the transformer libraries is if you want to run the model which you have trained, right, you have to again use this pipeline object to create this pipeline, okay? And the output of this pipeline function is a pipe object. This is what is used to run the model, okay? So normally in Keras, what we would do is we would simply say model of this, right? But here we have to say pipe of this. And pipe of this is exactly what we expect this to be. So now we will see if this sentence and the sentence that we'd seen before are the same, right? Let's quickly check that. Let me go up, scroll up a bit. What I have to look for over here is this one, right? Module and plugin. Let's see if module and plugin issue has been fixed. So let's go back down and see if this is now giving me module and plugin. Yeah. So now this is giving me module. So earlier this same translation module was saying plugin instead of module. Now it is using the correct word over here, right? So to some extent we have seen that this retraining this, right, has improved the prediction accuracy. So now the question is, how do we measure this translation accuracy so that we can report our scores to somebody, right? So the way we do it is blue score. It's a way to quantify effectiveness of machine translation. The meaning is bilingual evaluation understudy, and it solves problem of different human translation references by different annotators when generating machine translation. Like I said, the way the score is computed is there will be sets of grammar rules, right? So there will be +1, -1 for each rule that it follows, and then based on that, it's going to give some score. So that is broadly how it works. So we're going to load this metric from Sacreblue. We're going to see what the metric is for our data set, right? It turns out that the metric for our data set is 50, which is kind of bad, right? If we just go back up, in fact, we'll do it over there. Yeah, this one. The lower the score, right? The lower the score is better. The state of the art is the higher the score, the better. Okay. It turns out the higher the score, the better. The state of the art is 41.8 for those huge data sets. For our data set over here, we have achieved a score of 50, which is actually pretty good. So it turns out that retraining our model led to much better blue scores. Okay, cool. So this is an example of how to use the transformer library to do something like machine translation. Before I move forward, let me quickly take Indradeep's question. In transfer learning with Hugging Face transformer, we freeze training for some layers like in CNN. We have an option to do that, yes. So I will show you when I'm showing you BERT code, right? So guys, I think I'm going to require at least 10 to 20 minutes more. I hope that's okay with you guys. I will require 10 to 20 minutes more to cover BERT's code. It's going to follow the same lines. So I request you to be patient today. Just please stay with me. We will discuss this properly, right? Okay. Before I move on to the other application, right? Before I move on to the BERT application, I just wanted to list out one more example over here. Okay. Another example over here is this one. We're going to use we're going to use a transformer architecture, a pre-trained transformer architecture to solve the problem of summarization. Do you guys remember how bad our summaries were from LSTMs? You guys remember that? Okay, cool. So this is an example of an improvement on that. Remember I told you if we break it, we'll fix it. This is an example of how to improve on that. Okay. So let's quickly read this text. Time I want, so this is basically an interview between Donald Trump and this Time magazine. So I wanted to begin in the news. Iran overnight said it was considering enriching uranium at levels that would violate the 2015 nuclear agreement. You've been very clear that you won't let Iran get a nuclear weapon. Yeah, I think they'd be making a big mistake by doing that. Are you considering more military action? I wouldn't say that. I can't say that at all. It would be inappropriate, but they would be making a big mistake if they enrich. And this is Donald Trump being Donald Trump. He's making veiled threats. So yeah, then we have, are they calling your bluff on this, or how do you see it? Time will tell, only time will tell. Time says, I mean your campaign, you promised to get the US out of unnecessary foreign wars with your dash. That's true, well I have. So this is Donald Trump messing up an interview as usual. So now let us see what summary we get if we simply use a summarization pre-trained model. Okay. Iran is considering enriching uranium at levels that would violate the 2015 nuclear agreement. Donald Trump says it would be a big mistake for Iran to enrich uranium, but he's not considering military action. Do you think this is an excellent summary of whatever we read so far? Okay, cool. So this is a very convincing example that transformers solve all the problems that we have encountered with LSTMs and GRUs before. Okay. If ever in life you are required to solve an NLP task using transformers, my recommendation is go to this Hugging Face library, check this documentation for doing it, and then use this. The pre-trained models themselves are doing so well. We didn't do any retraining here. So please make sure you explore this library. It's kind of fun. So I have been working on the side project where I have a bunch of papers and I want to extract certain information from them, right? I'm trying to see if I can use these pre-trained models for doing that. So I highly encourage you guys to take up these tiny projects and get them through, right? It's very good for the confidence. So yeah, okay, cool. So now let's use the same library to apply BERT to do named entity recognition tasks. Okay. So the task that we're going to get BERT to do now is identify all the diseases which are there in the papers which are given to us. Okay. That is the task we are going to be training BERT on. So let's see how to do this. So let's come here. The main thing that I'm going to need to import this time is BERT tokenizer and TF BERT token classification, right? TF BERT for token classification. So over here in this documentation, you see this problem, right? Token classification. All the code which was written here now is basically coming from this documentation. Okay. All the example code is basically picked up from here. This one is on the data set we studied 2 classes back, right? We applied LSTMs to solve this problem. But today we're going to use a different corpus to address BERT's problem. Okay, cool. So let's see this. So the data set I'm going to have is this NCBI corpus training, NCBI corpus development, NCBI corpus testing. So for those of you who don't know, NCBI stands for National Center for Biotechnology, Biotechnology Information. So this is like a US-based organization which collects relevant medical papers and annotates them. Okay, so they have created this corpus where you have different types of text. Okay, and you have these labels associated with this. Okay, so I want you to specifically pay attention to this one. So this label that you see here, right, is basically indicating that the next few words are specific diseases. So let us try and make more sense of this now. Okay, is everyone in class familiar with what these are? HTML tags are? If not, I'll give you an example, right? I'll first quickly give you an example of what an HTML tag is. So in HTML, right, basically, let us say you want to make a text like the best neural network architecture, something like this, right? Let us say this is the title of an architect. This is the title of an article. If you want to tell the web browser that you have to make this part bold, what you have to do is you have to say font to bold, something like this. Actually, no, \B will do it, right? B and \B. So I believe this will do it, right? So, strong will do it. Yes. Thanks for that, Indradeep. It's been a long time since I've done HTML. I don't remember this stuff. So strong will do it. Okay. So why I wanted to discuss this is generally when we want to associate special parts of the text with something, right? We put these words over here. So these things are known as tags. Okay. This is a way for, this is basically a way for your browser to understand that something special has to be done with the text here, right? So the way a tag works is there will be this open brace, close brace, which is the angular brackets. Then you have this backslash over here, which tells you that this is ending now. Okay, so the backslash over here tells you that it's ending. So the same way over here now what we have is we have category equal to special disease followed by the name of the disease. And once that disease is done, there will be a closing tag. Okay, so let's see a proper example of this. By the way, this is what the word count distribution looks like. It's fairly Gaussian, so don't have to bother with this for now. What I want to show you is how annotations are done in this text. Okay, so you have category equal to special disease, HD, right? Here HD stands for Huntington's disease, by the way. Okay, so category special disease, Huntington disease, followed by backslash cat or forward slash category. Okay, so these guys are using forward slash category. I guess these are interchangeable. Backslash won't work, right? Actually, backslash means escape. So my bad. It was supposed to be forward slash here. Yeah. So yeah, backslash won't work, right? Because it's escape character. So yeah, this will work though. So this is how the tag looks like in our corpus. Okay, it's already tagged for named entity recognition. So basically what this dataset contains is it contains something which is known as a modifier. It contains specific disease. It contains disease class and composite mention. Out of all of these, what we are interested in is the specific disease. Okay. So what we are going to do now is we're only going to keep these tags and get rid of all the other tags. So the rest of this pre-processing that you see over here, right? It is just to get rid of all other tags. And instead, what we're going to do is whatever is labeled as specific disease, right? Whatever is falling between these two tags, we're going to extract that information and we're going to create a new column in our data frame where the labels are all the diseases which appear in this training text. Okay. All the diseases appearing here will appear as labels. And we're going to train our model to basically recognize these labels from the text. Okay. So now all the pre-processing is getting done over here. Before pre-processing, it looks like that. So look at this. There's this modifier in category, right? So that is removed after pre-processing. Okay. So all the tags are removed over here and the labels that are extracted are shown over here. Okay. So this is what the pre-processing parts are doing. Moving on. Now that we're done pre-processing our data, let us actually use BERT to do this task. Okay. So to do this task, we have to specifically look at how to carry out this. We have to sort of see how this class is implemented, right? BERT for token classification. So there is this class now called BERT for token classification. You have to see what rules this follows. So the way this BERT for token classification, what this expects is it expects labels. Okay. So the labels that we're going to use are going to be O's and B's. So B over here means beginning. So I'll give you an example of what we have to do now to convert this data frame into a data set which we can use to train BERT now. Okay. So before we can apply BERT on this, we have to do one more important pre-processing step. That is convert this into a format which BERT will understand. Okay. So it's very obvious what we have to do. We have to take this sentence. Okay. The intersex differences in colorectal cancer risks have implications. The word tokens look like this. BERT tokenizer will give the following indices to these numbers. What we have to do is write some code so that we can generate this kind of training label, right? So the intersex differences in all of these words have to get O's, right? Then colorectal cancer, it's colon, right? So colorectal cancer will be BB. and then we have risks have implications will be OOO. Okay. So what we have to do now is we have to write code which will do this kind of thing. Okay, cool. So that is what all of this code is now going to do. I'm going to skip this part. You can check it out later. All that these two functions are doing is it is going to convert the data frame into a series of tokens and corresponding labels. Okay, corresponding labels. So one more additional step that we have to do is we have to assign numbers to these O's and B's, right? Yes. Indradeep, it's not binary, it's ternary. There is one more. You see this P over here? We need to see this P also actually. So the P over here means padding. So O means not word not of interest, B means word of interest, P means a padding word. So we have to do 3-level classification. So it's a multi-class classification problem, 3 classes. Okay. So what these two functions are now going to do is it's going to assign labels like this. Okay. So O is going to have label 0, B is going to have label 1, P is going to have label 2. Okay. And that is how we're going to do this. Okay. So once we're done with pre-processing our data set, we're going to import NLTK. We're going to use the NLTK tokenizer to do all this. We don't want to use BERT tokenizer for this, I believe. No, 1 minute. Why am I using NLTK here? Let me just check. Train labels, labeling of data set. No, this labeling function comes from transformers library. Pad sequence label also comes from transformers library. What am I using NLTK for here? Punct is what I'm using it for. Guys, all these functions, right? We're using functions from this. We're using functions from transformers. We're not applying NLTK here. I'm not sure why we imported NLTK. We'll see later on. But this code block, right, tells you how the tokenization part is working. So if you're confused about how tokenization is going to work, look at this code block over here. So the sentence is complete absence of C7 was also found in one sibling who had clinical syndrome on blah, 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 right? So the tokenized sentence, when we apply NLTK's tokenizer, I believe, no. This is tokenization at the first level where we break this sentence into different words. So what we're using here is actually BERT tokenizer. How do we know BERT tokenizer? Because of this double hash coming here, right? So this is BERT's tokenizer. Then the sentence IDs are over here. This is converting these to numbers. Then we have the token IDs, which is zeros everywhere. And only when we see ones over here, we will see the this thing, right? We will see the ones. Ones will be the diseases over here. So our labels will have ones wherever we are storing the disease names. Okay. So this is what this will look like. So why do we have so many ones here? Let me quickly show you. I was also confused by this, right? The reason why we have so many ones is because of this thing. Meningococcal meningitis is actually split into many different tokens. So you have men followed by inj, then meningocco which comes, and then ka which comes here, right? And then L, then you have meningitis. So 3 tokens for this. So that is why we have so many ones over here, by the way. Okay. And at the end of the sentence, you will notice that we have 2s because these are simply paddings for the rest of my sentence. This is because the input vectors have to be of a fixed length, right? So that's why we have these padding tokens. So now, essentially, this is what we have. Token attention masks are, yeah. So these are attention masks for our tokenizer. I guess we're going to use this somehow. Let's see. So now at the end of this, once I finish my entire pre-processing step, I get this kind of a matrix. Okay, I get this kind of a data frame. Now that I have this data frame, we can go ahead for training, right? So let's first split this into train and test and validation so that we can make sure our training is working properly. That is what these code cells are doing. How are we going to train our model? We're first going to use this class, right? TF BERT for token classification dot from pre-trained BERT base uncased. So we're now going to load BERT base uncased to do retraining on, and we're going to apply this to do our task. So now let's see our NER model. I have my input IDs, my token type IDs, and my attention mask. My embedding is basically all this, right? My embedding is basically this. My output logics are dense of tags to IDX. This is just the output layer. Embedding is encoder. So encoder is basically this BERT encoder. The output of this BERT encoder is going to be an embedding. What I'm going to do is I'm going to take this embedding, apply a dense layer on it, right? See, I'm passing this embedding to this, right? So I'm going to apply this dense layer on this. And finally, the output of this dense layer is what I'm going to consider as the output of my model. So this is exactly like transfer learning, right? Okay. So Indradeep asks me, why do we have attention mask in the embedding layer? Uh, so this is one of the things which is required when we are doing token classification. So this is one of the things that this expects. Okay, Indradeep. So the way BERT was trained was with this one. Wait. I have to download this fast. Download a copy. Okay. No, the reason I just had to download this because once this connects, right, it gets rid of all the outputs over here, and I want you guys to have the outputs of a of end-to-end run notebook. So just wanted to do that. Sorry, let's come back here. Now, one of the requirements of BERT is this attention mask. So it is. So let us just go back and see what this attention mask is. Huh. All the tokens from the sentence are marked as 1 and the padded tokens are marked as 0. Marked as 0. The reason we want the attention heads to pay attention only to the token in the sentence and not the padded tokens. So Indradeep, do you remember that we were discussing this masking process over here? So this mask, attention mask, right, is basically going to help it put minus infinities and infinities in the right place. So what it's going to do is it is always going to mask the padded tokens. So that is why we have to pass this. So all this attention mask is doing is it is telling us how many words in this sentence are actual words and how many of them are pads. Does that make sense? Okay, cool. So moving on, we are passing this attention mask for this input to our model. Then we have our optimizer, which is Adam with a learning, very small learning rate, right? 3e minus 5. Our loss is basically sparse categorical cross entropy because this is multi-class classification. And then we're going to compile our model. The summary of our model looks like this. We have input layer 1, input layer 2, input layer 3. We saw what these were. These were basically the input IDs, the token type IDs, and the attention masks. Then we have this TF BERT for tokenize token classifier. This has many different parameters. So all of those are listed out here. Then we have this dense layer. And finally, we have our output. Okay. So we essentially go ahead with the training. We train this for how many epochs? We train this for 5 epochs. And we add callbacks for saving the checkpoints, right? And essentially, this is how the training goes. Let us quickly see what the training accuracy and loss curves look like. So my accuracy curves look like this. My loss curve looks like this. Can anybody comment anything about overfitting, underfitting here? Is this overfitting? It's not obvious, but slight overfitting is there, right? Slight overfitting is there. So like the training scores is the higher than validation. So maybe it's not exactly overfitting. It's better than the other models you've seen, but there is some amount of overfitting here, right? And the training accuracy is also pretty good. So let us look at our validation accuracy. Our validation accuracy, our final validation accuracy is 99.76, right? So this is excellent. So this is the advantage of using something pre-trained like BERT. It will already have a lot of knowledge about these different tokens. We can leverage that knowledge to make our tasks easier. So this is like pretty amazing results, right? So now what we can do is we can essentially get a prediction for our sentence. So let's see an example over here, right? Let's see what the so essentially what these code cells are doing now is it is going to go back and predict everything in our validation data frame. Okay, so we actually get all the keywords from this. Okay, so let's see all the words that we're getting. Okay, so heredity ovarian cancer sounds like a disease. Ovarian cancer sounds like disease. Piebaldism sounds like a disease. Histidinemia. Okay, that sounds like a disease. Myotonic dystrophy also sounds like a disease. So it looks like our model is doing pretty well, right? By looking at these results, it is able to extract disease names from the sentences which are there, right? Okay. So that completes our coding example from Hugging Face Transformers library. Okay. So to summarize what all we saw today, we saw how a transformer architecture works. We saw how BERT is an encoder only architecture. We saw how to use this transformers library from Hugging Face to implement not only transformers but also BERT. Okay, this is the go-to library for us. And we also saw why it's not practical to sort of train BERT from scratch, right? So that's kind of summarizes all the content that I had to cover in this NLP module, in fact. So I'm actually done with all the content which is there. So cool. What I'm going to do now is I'm going to just do a quick revision of everything. Like I just want to give a quick overview of what all we have learned and what all we should be confident with, right? Once I finish that overview, I'll just give you some pointers of as to how to move forward now, and then we can end the class. Okay. And of course, I'll be happy to take any doubts that you may have. Okay. So closing remarks for this module, let me just make them. Okay. So guys, broadly what we have seen is we have seen how NLP has evolved as a field over the last 10 to 11 classes. Okay. We basically started out with heuristic methods, right? We started looking at what people used to do before deep learning entered the picture. All the heuristic methods basically relied on handwritten knowledge bases, right? You required humans to actually come in and use grammatical rules or their experiences to create these data sets from which things used to be done. So most heuristic methods relied on human intervention for useful information from text. So heuristic methods basically required a lot of human thought and a lot of humans to put in rules which may or may not always be satisfied, right? It's impossible to create a set of rules which will completely define a task because of the ambiguity which is there with text. So then one way to tackle that ambiguity was probabilistic models. So we saw things like naive Bayes, bigrams, trigrams, all those things, right? And CRF, like conditional something field, right? We saw these methods, which essentially give us probabilistic ways of dealing with generating rules. Yeah. CRF was conditional random fields. And naive Bayes, right? And finally, since the RNN class, we have seen neural network approaches. Right? And broadly, we saw that most neural network approaches are somehow inspired from these heuristic things that we saw and the probabilistic things that we saw, right? So the main takeaway that I want you guys to have from this is it's kind of important to know how things came from here to here, right? Broadly, that has been the focus of at least my style of teaching has been how do you connect heuristic and probabilistic methods to neural networks, right? How do you get inspired from these things to generate architectures over here? So broadly speaking, when you come to deep learning and you're learning deep learning methods, right, it's very important to always ask yourself, where is this coming from? So at any point, if you're reading a deep learning paper or a neural network paper, remember that there is probably a concept from heuristics or probabilistics methods which has inspired this approach. So it is a little bit painful, but try and make it a habit to link whatever you're reading to some other concept which came before, right? This type of thinking will basically train you to recognize how to debug stuff, right? Because even when neural networks fail, right? See, what are we training ourselves for? We're training ourselves to be engineers who can debug and fix issues with neural networks, right? So, the advice I'm trying to give you is the best way to gain confidence in debugging is to have a mental map of where this comes from, where this technique for neural networks comes from. Because once you know that connection, you can use strategies which people have used to fix these problems over here, right? That is how you get creativity. You can be creative while problem solving if this link is clear to you. So that's the idea. Quickly, let me check Indradeep's question. We use LDA for topic modeling. How to use deep learning for topic modeling? Any good pre-trained model? Yes. So topic modeling in itself, I guess, is one of the tasks here, right? Causal language modeling. Yes. This is frequently used for text. No. This is text generation. Multiple choice. What is multiple choice? Okay, multiple choice task, right? This is not multiple choice task. To some extent, it would be like a summarization task, right? Where you are setting the summary to be one or something like that. So topic modeling, I believe, is not. So I'll have to look into this. I'll have to see where topic modeling fits among these tasks, right? And then we can go for that. The thing about LDA was it used a probabilistic way of generation, right? The reason why you won't have an exact correlate because generation is being done by, so whatever LDA was doing there, right? Think of it this way, Indradeep. Whatever LDA was doing for us there is being done with a pre-trained decoder now, right? This decoder is doing the job of LDA there. So we have a much better way of getting things. We have a much better way than LDA for doing things here, right? So if you ever feel like you need to replace LDA with a neural network architecture, go for a transformer decoder. Okay. So I believe LDA topic modeling will come somewhere in question answering. So I guess you can somehow think of how to convert an LDA topic modeling task to a question answering task, right? Where the default question is, what is the major topic of this document? So maybe you can train a question answering network and get the answer to that question. So that's one creative way of applying that, right? Okay. Coming back to concluding remarks, what I want you guys to focus on is if you know the link of where in over here in the neural network part, if you know the link to where it has come from, right, you can generally debug better. So my advice to you is by no means are you guys ready to probably face industry level tasks today. What you will have to do is a little bit of projects on your own side and a little bit of experimentation with all the code that has been given to you. Okay. So I just want to give you some idea of what you can do to sort of make yourself competent, right? What you can do to improve in this area. One thing is go back and play with each and every notebook which has been given to you, right? Each and every notebook. The good thing is we have compiled all the code and it's working, right? So we have made sure that the code is working. I want you to play around with the code that has been given to you, and I want you to try and memorize the code. Okay, that is step number one, where you know if there is a task, how to do that task. Step number one. Step number two is do a personal project where you're applying the concepts and try to gain confidence in the fact that you can now solve small problems using whatever you have learned. Once you gain that confidence, I want you guys to then start participating in maybe Kaggle competitions or start reading papers. So you can do it both ways. You can either read papers, you can discuss with each other, you can discuss with me, etc. Or you can sort of attempt competitions and gain confidence that you're competent at a global level, right? So these are the steps forward from this course. Okay. These are like kind of the closing remarks that I wanted to give. I wanted to make sure that you know where to go from here. And always remember, I'll be available for chatting and whatever on Slack. I'm always interested in different problems which people try to solve, right? So if there is a task which you need my attention towards, which could take like less than an hour, maybe Slack would be a good option. If you think the discussion will take more than an hour, you'll have to ask me for a slot and we can set up a slot either on the weekends or something, and we can discuss then, right? So that's how we can move forward. And yeah, apart from that, all the best. I sincerely hope whatever I have taught you from computer vision and NLP will be useful for you in your careers, if not at least in your personal projects. And I wish you all the best of luck. So with that, I'm done with the content for today. And yeah, so if you just, so guys, I may not know your names personally, right? If you tell me you're a Scalar student, either on Slack or on LinkedIn or any other places, I'll be available. I'll make myself available. Okay, that's my promise to you. So that's what. Cool. Okay. Nice to know that, Tim. Thank you. Arun, I'll be sharing the cheat sheet soon. NLP. We have a cheat sheet. It's just that I'll have to request the official channel to do this. So yeah. Thanks, Anil. Thanks. Okay, one quick question. How NLP can be used for labeling images? In CNN first class, we had an image of train. Yeah. Perfect. So Indradeep, there are these models which are based on transformer architectures, right? So think of it this way. You have one transformer encoder sitting here. You have one CNN sitting here. Both of these are feeding representations into a dense layer. Okay. And then that dense layer's job is to connect or to create a mixed embedding. Okay. So broadly speaking, think of this kind of a Siamese network where one part is this thing. Arun, OpenCV OCR will have the old techniques, right? It will have heuristic and probabilistic methods. But what Indradeep is asking me is, oh, you can't see my screen. Just 1 minute. I'll stop and restart sharing. Is it now visible? Is my screen visible now? Okay. So I'll tell you how these multimodal networks work. Okay. The first few multimodal networks basically they merged an RNN and a dense net, like ResNet like thing. So think of it as taking ResNet, taking an RNN, and then the outputs of these two are fed into a dense layer, and the dense layer's job is to connect both of them. So what they did was they did these mixing and matching of different architectures to get the job done. Then the more recent ones are purely attention based ones. So there is a way for you to implement attention using vision transformers. What they do is they take that vision. So there is something known as squeeze and excite block, if I am not mistaken. It's actually a very simple concept. So if you're interested, I'll just quickly tell you what it is. Okay. So imagine you have this ResNet block here, right? Conv, relu, then batch norm, followed by conv, right? So this would basically be one block. You will have a skip connection here, right? So the way squeeze and excite network works is that it will use this convolution output to generate attention weights. How it will do it is, it will go to this one, it will use this as the querying key, it will apply this querying key to this convolution output as the value, okay? Once it has done this, it will reweight all the features of this convolution output and then pass it forward, okay? So broadly speaking, this is how squeeze and excite attention blocks work in convolutional neural networks. Now what people do is they will have a mixed sort of network where one set of inputs is the image, one set of inputs is the words, and these go and fit into a common attention mechanism, right? And that is how these mixed embeddings are obtained. So that is like a little bit of intuition. I'll point you to some papers if you're interested. And it is these kinds of networks which will do the task of labeling images. Yeah. Cool. So there is one question which has been asked. I'll quickly answer that. More info on the advanced NLP course, high level syllabus. So Anil, the broad idea behind the high level course is to train you on ChatGPT, how it was trained, and on tools which are coming around ChatGPT, right? You may have heard of this thing called prompt engineering and all that. So there are these libraries which do automatic prompt engineering. So the main objective of that course will be to train you to use that library. which does automatic prompt engineering. So broadly, that is the content of that part of the course. It is still under design. I'm not sure on when the course will be ready, but it will be communicated to you, and we'll make sure that you have a chance to attend it. Okay. Verma sir will mostly be taking that part. So yeah, cool. So I'll mark this question as answered, and yeah, we can sort of end the class here. Guys, please stay in touch. I'll always be interested in how you're doing. If you have any kinds of discussions, please feel free. So yeah, that's all. That's the closing thing. Anil says, okay, do we need to do anything from our side for that? Anil, be very confident of how to be very confident about BERT and transformer architectures, because Chat GPT is like a decoder only thing, right? So what I will suggest is study this notebook which I'm going to attach today and this notebook which I'm going to attach today. These two, if you study, right, you'll be more than prepared. The main thing is to understand how this attention thing works. If you understand the attention thing, you should be ready. So yeah, cool. Okay, guys. So wish you a very good night and wish you the very best of luck for your endeavors. Uh, Thank you for being a wonderful audience, and I'll see you again. Good night.